So welcome everyone to the second webinar of IDS. We have today two very interesting lectures, presentations, and we hope we will learn a lot about the efficiency, energy efficiency, and desalination and reuse plants by our guest, Jesus Rivas from WEG, and Juan Cifuentas from Energy Recovery. Thank you both. It's a pleasure having us, a pleasure and an honor having you here at this IDS webinar. And I also want to welcome Professor Jack Gilleron, who is our moderator today. So I will let Jack present, start with the presentation. Thank you very much.
Thank you very much, Miriam. It's really good to see so many people joining in from all the different regions and occupations involved in the IDS. Our talks today will be on the theme of energy efficiency and ways to increase energy efficiency in desalination. Before we start, just a couple of housekeeping rules. I would ask everyone for the course of the presentations to mute yourself. Also put your cell phones on silent or vibrate, and turn off your videos. The way we will do questions is each speaker will have about 35 minutes, and then we will have 5 minutes for questions and answers. And the way we'll do the questions and answers, since we have so many on the call, is I would ask you to write your questions in the chat, and then I will read them out and ask the speaker to answer. If we have time at the end, we budgeted extra time, we can go back and catch those questions we aren't able to do after each speaker. So without any further ado, we'll start in. Our first talk will be from Jesus Rivas from WEG on various strategies for getting to energy efficiency and desalination. And just a brief background on Jesus: he's trained as an industrial and mechanical engineer. He has an MBA. He's been working in the water treatment industry for more than 20 years. He began with Veolia in 2001, and he's worked on a wide variety of water treatment and desalination projects around the world. So with that, I will let Jesus begin with his talk. Go ahead.
Okay. Thank you for having me in this presentation. Thank you, Jack. Thank you, Miriam, for this invitation to IDS webinars. So, with no more delays, let me share my screen, and let's go to the presentation.
I'm sorry, I'm the only one that hear your voice very bad.
No. There is. You have a problem maybe with the earphone or with the connection, because we cannot hear you well, Jesus.
No? Okay.
No, there is a noise. Maybe there is a cable or something. Try to speak again.
Okay. Can you hear me now?
No, there is a noise.
Let me disconnect.
We can hear, but there is a noise.
So maybe this is a problem with the... Okay, let me...
Me parece que son los auriculares.
Miriam, can you hear
me?
Much better. No. Wait.
Much better, but not enough. There is some metallic hum on the voice.
Was working before?
Now it's perfect. Now it's perfect.
Now it's perfect? Okay,
Yes.
can you hear me now?
Yes,
Yeah,
yes.
much better.
That's good. Okay. Okay. So let's go to the presentation. I don't see the attendees, but good afternoon, everyone. Thank you for your attention to this webinar. We are here to talk WEC. I'm representing WEC here. We are going to talk about how we can help to increase the efficiency in desalination plants to reduce the electricity consumption. Very briefly in this webinar, I will introduce three main blocks. At first, a very brief presentation of WEC company for those who you don't know yet. And then we will move to the central block where we will talk about how we can optimize the efficiency and effectiveness of the water treatment plants, desalination plants specifically, with high voltage motors and medium voltage drives applied to a practical case. We will see the importance of increasing the efficiency of the motors and the economic impacts they have. And at the end, I will give a quick overview of the other solutions that help efficiency in other water treatment plants. But let's go ahead with this short introduction to the company. Okay. WEC is a company based in Brazil, specifically in the south of Brazil, in Jaraguá do Sul. We are a company with more than 40,000 employees. We have factories around the world, and we are listed in the stock market with a very good financial reputation in Brazil. But in these figures, what strikes me the most is not only the size of our industrial plant we have in our headquarters. You see here below, above 1 million square meters. This is very impressive, but this value of 60%, almost 60%, is what we sell of our products that have been launched and have been designed in the last 5 years. So this gives us an idea of being a company in continuous evolution and development of all our products. We have more than 50 factories around the world in more than 15 countries and business separation in many, many countries. So in almost every country, you can find a WEC branch or an official WEC representative. What supplies WEC? WEC supplies all type of electrical machines. We are very well known for motors, but we supply electrical machines, automation for all industries, from power generation to transmission and distribution, electrical automation, equipment, switchgears, electrical power and control panels and cabinets, right down to the smallest motor you may find in your washing machine at home. Okay. We are also in solar, wind, renewable energies with generators, in digital solutions. We have digital solution division with artificial intelligence, improving automation of industries and machines. We are also active in electric mobility with EV chargers for electrical vehicles. For instance, we are known for the powertrain for mobility for electrical buses. And WEC is also following the big market trends, which are currently the energy efficiency, which is the object of this webinar, renewable energies, digital solutions, and mobility. Okay, so this is a brief introduction. Here is a link where you can see in a YouTube video to introduce, and you can see more the business units in the company. But let's skip that to go faster to the presentation. And if you don't mind, you can copy this link and see after that. Let's go to the main part of today's presentation. In this presentation, we will show you some ideas of how we can help the water industry and desalination DPCs to achieve better efficiencies. Okay. Our idea is a holistic idea, is to work in close collaboration with engineering EPCs and EPCs, constructors, to better design the water treatment plant. We could say that success is also based in our commitment to give support from the conception of the project. And also based on the knowledge that, in our knowledge of all types of water treatment plants, not only desalination, but also pumping station, water transportation, irrigation, and so on. So we try to collaborate in partnership with EPCs. The why is clear and how is the way to work. You see here, we close the circle. We are doing engineering, design, project management. We involve also our teams of R&D, manufacturing. So all disciplines here, when you are defining a project, all disciplines are coordinated from the start, from the EPC. And the results are good. That these results in a good procurement, a good equipment, and solution that has to be proven during the commissioning phase. In the end, to get water treatment plants that meets and delivers the highest reliability and best performance, having a better efficiency, lower operating costs, this also is translated to a lower tariffs. Here you see the object. This is the EPC purpose, the developer, the end customer at the end. But when we are trying to work like that, in this way, two things can be achieved. First, winning contracts. In these demanding types, is difficult to get contracts, and to win a big contract is very important. These values of the types. And also lower the energy consumption, and consequently the lowering the carbon footprint. That way, and with the goal in order to be more competitive in the definition of the desalination project, when looking for the equipment, the systems, and taking into consideration the aforementioned integration of engineering, it helps a lot to be integrated in the project from the very first beginning, design, start moment of the plant. We can study the PFD, the process flow diagram, the PNSDs, the distribution of the equipment, the loads, the electrical loads and consumer. You see here a PNID with a lot of different motors, maybe different electrical areas, electrical rooms, the influence they have in the calculations, the hydraulics and civil works. All this has to be considered from the starting point. We are with you. So we understand the process, and we can help you with the single line diagram, the list of electrical losses, and many other conceptions, voltages, what kind of consideration you may use in your design, engaging all disciplines. So that's the point. This is the holistic view of the approach from WEC in this water segment. And now we are going to be more specifically. We are going to talk or to see more specifically the most effective application when we try to reduce energy consumption in a big desalination plant. The most important and what affects the most is going to be medium voltage drives, the variable frequency drives, and the high voltage motors. These two solutions, equipment that are always needed for the RO process of the plant, they have both of them usually they have the big impact. Then there are other solutions and auxiliary systems for the water industry that I will talk about very briefly at the end of the presentation to give you a rough idea. But let's focus now on the motors and the medium voltage frequency drives. Okay, so there are some points to consider. Pardon me. In the electrical engineering support, we consider many technical aspects. This is, you can read this more carefully later, but you may have heard about transformers inside, outside, cooling ducts, electrical load balancing, and so on. But when we start to consider the electrical engineering of a desalination plant, we have to consider many important aspects in order to get off to a good start. For example, the type of motors, the current design in the market, what are the starting methods? Okay, soft starter, frequency drive, DOL. We also have to look at the economic aspect of how much the motor and the VFD will cost and what design can influence the cost the most, such as, for instance, the supply voltages, the cooling methods, or if we are going to require any special test to validate the systems. All this has the influence in costs and decisions for the engineers. Some factors affect the efficiency and cost a lot. supply voltage, I mentioned that before, safety margins that we are going to consider between the motor and the pump. This is crucial in some times. The insulation of the motors, what is required, the service factor. So many technical factors, many technical aspects that should be considered. Also, the complete system may have to do an harmonic analysis. You have heard about the total harmonics distortion. We have to design a specific motor and drives and make all these calculations that are more appropriate to the duty point that we are actually going to have in operation. This means that you are not going to have only one point. Nowadays, we are looking for several points in the curve of the pump and the curve of the motor that has to be guaranteed. If we going into details, when we have to select the high voltage motors for a desalination plant for the RO process, the motors, for example. The motors, typically our model is the W60 model, which is the most used, but there are some other types depending on the size. W60 for the RO plants, the high pressure pump is, their power ranges from 1 to 7 megawatts. Let's say normally now in bigger plants, we are talking about 6 megawatts for the high pressure pump, and for the feed low pressure pump is 2, 1, 1.5, something like that. So with this slide, I would like to show you how difficult and how many parameters our engineers and sales people has to manage to give you the proper solution. When our engineers have to define the motor, they have to define in order to achieve the best efficiency so that the products are economically viable. At the end, they have to make a configuration project of the motor. The motor is made to measure for each desalination plant. Each motor has different services, but in all of them, they have to look for the technical and economical balance, okay? Because at the end, you are going to buy and you are going to pay for that. And we have to take all this in mind. When it comes to achieve the best efficiency, it's basically a matter of reducing losses, okay? Less losses, more efficiency, that's clear. Okay, so the number of poles and the frequency are also taken into account because they have influence in these losses, mechanical and electrical losses. If we go to this area, to the losses, we can, I try to resume the effects or the electrical and losses. For instance, the Joule effect losses. You have to look at the coil, the plate slot format. I see the metal sheet is stamped in the metal plates to house the coils. You have to consider the shape, the model, even the copper wire diameter, the air gap, or even the film effect that happens when you lower the frequency. So this determines the Joule effect losses. In the iron, the losses in the iron, we have to look for the place material, the stator and the rotor of the motor, the rotation of the grain. All these effects, there's not the same materials. There's not always the same materials, and you have to consider what is the best solution to allow higher magnetic flux, okay? For sure, there are also supplementary losses due to margins in the standards, and then the mechanical losses, which are losses due to friction and ventilation in the bearings and the heat exchanger, and especially in the internal fan, which is the one that affects the most in these mechanical losses. So this is a short presentation of the points for the motors. Okay, it's just to consider all these points. Normally, we don't pay attention to these sneaky points. Okay, the same for the medium voltage drives. Okay, you allow me to drink a little bit. Sorry. When we are defining the medium voltage drives, the VFDs, we have two models, the MBW01 and MBW3000. There are different parameters that really affect the calculation. We are not presenting this this is not a commercial presentation, this is a general technical overview. These factors, one is the supply and output voltage. Okay, this is clear. By selecting the proper supply voltage, you can decrease the cost of the components. The ambient temperature where the drives have to be located, this is important, is the ambient temperature to calculate this efficiency. The air must be filtered. This is something that the location must always be taken into account. We also look at the type of motor that the drive is going to feed, because you have to know what insulation has. The motor has to be ready, has to be prepared to be fed by a VFD. We consider the distance of the wiring from the inverter to the motor, although in water plants, this is not usually a problem. It's usually, they are normally quite close, less than 300 meters, so there's not need for filters, and it could be the case. We are also going to look at the different drive topologies. We build the two topologies in the market, the cascade topology and the central point topology. The difference is whether the inverters, the IGBTs, are going to be in medium voltage or low voltage. We have the two models, the MBW01 model with the medium voltage IGBTs, and the MBW3000, which is more common in water segment, with the low voltage IGBTs. We are also looking for the cooling system of the drive. Normally it's air, but could be other special types like water. We have sold some VFDs water cooled. Another point that affects efficiency is the material of the input transformer to this drive. Being copper, aluminum, even improved aluminum, we have different efficiencies, cost and efficiency. This that we were talking before. But for me, with this holistic idea, the most important thing about this configuration is the motion drive itself. Look at this looking at the whole electrical schematic configuration with the medium voltage switchgears that feed the drive, and this in turn in the motor. Medium voltage switchgears, the drive, and the motor. By looking at the voltages and the powers, we can optimize the investment prices and the efficiencies of each of these parts, so that together they give the highest efficiency and the best possible cost. This is the reason I was talking before about this holistic idea and support the engineering from the beginning. And to show the influence of this efficiency improvement in motors and drives, we will see now an example of what typical in a typical desalination plant. Okay, this is going to be the more attractive part of this presentation, I believe. And the reason is that I don't know if I'm run out of time, but you can see here this advice and graphic where you see that the OPEX, the breakdown, the electricity consumption represents the largest part of this OPEX. Almost 44 or even more percent is the power in a desalination plant, and even in a wastewater treatment plant, for instance, the electricity consumption 55% is taken by the blower. So it's an important issue. Let me try to present this test, if it's possible to open an Excel file for you to see this course that you already may know, because you are the experts, you are the process guys, the PCs. So you are always wondering.
Jesus, people are asking if you can enlarge a little bit the pie chart.
The pie chart?
I don't know if you can, but I don't think you can do it now, right?
I have now presenting the Excel file. Can you see that Excel file?
Yeah, yes, we can see, but the numbers of in the pie chart is.
We don't see the Excel now.
You don't see the Excel?
The Excel itself, no.
Okay, that's a pity, because that was.
You can, Miriam. This is what you're looking at now is an Excel thing.
This is the Excel or not?
You can see charts.
It's the presentation. Sorry, who is, sorry, please.
It's David.
Just let me tell, you are trying to open an Excel file, right?
Yes, this is an Excel file.
No,
no,
I don't see it. So you have to stop sharing and sharing the Excel. Okay.
Let me share the. In that case, let me share the screen. I will try to share the again, let me know when you can see my screen.
Yes, now we see the Excel.
Okay, you see that. Okay. Okay, much better now. Okay, these graphics, these correction curves is what the EPCs can prepare. You have at the end to calculate the estimated power consumption, in this case 3.60, depending of the TDS and temperature of the water. If you increase the conductivity, for instance, you see here the green line, the gray line moves, and the calculation the same. Okay. Also, you modify the water temperature by decreasing the water Celsius. The power consumption consequently increases. So this is what you are doing, and this is when you have to select the proper operating points for your plants. I'm going to present. You are still watching my screen?
Yes.
Okay.
Yes.
So in that case, I'm going to go to a more interesting part, which is PFD, what I saw you before. This is a typical Arrow plant. I'm going to start opening this Excel file, another Excel file. This is the typical desalination plant, not the inlet, the intake, the pretreatment, or the product water pump. So here is the first pass RO, second pass RO, the high pressure pump, the energy recovery device, the feed pressure, recirculation. So at the end, you have, okay, I hope you are seeing now my Excel file. Okay.
Yes.
Okay, good, perfect, fantastic. So I'm going to open it a little bit more. This is something your process people prepare with a lot of calculations behind. This is just to make a sensibility analysis for the motor. So I took the process and I have prepared here this kind of presentation for you to understand the improvements in efficiency. But when you have this, when you have calculated all these membranes, the pressure here, 60 hours, 40 grams per liter, this temperature, you can move that and you see the power consumption. This is the same, but let's focus that the calculation is smooth, even if we modify the temperature, and also if we modify the TDS. So the consumption could be reduced or increased, depending on and also the pressures here, if you pay attention to this also varies. So with this, and consider all the calculations you have for, these pumps here. I don't know if you can see that. These pumps, second pass RO, booster pump, high pressure pump, with all the calculation, the recovery rate for the first pass RO, split if you have decided with a split the RO1, the second pass recovery. For this plant of almost 600,000 cubic meters per day, for these pumps, I took my permission to make this analysis. You can calculate all these pumps, considering the motor efficiency, the absorbed power, if this is fed by a drive or not. I'm going to show you that all these calculations and all the calculations behind this Excel, you can summarize that. I have this presentation with only modifying this motor efficiency for the cartridge booster pump, the low pressure pump, the high pressure pump, and the second pass RO pump. I'm not talking about the drives. We will show you this later, or the other efficiency, transformer, the wire, all these calculations that your process and electrical people should prepare. At the end, gives you a power consumption. Okay, you can be here. Let's say that you are working. Sorry, because of the internet. Let's check to a standard. Pay attention to one example. 3 point something. Let's see if this is stopped. You have the power consumption here. Okay. I'm going to consider one project where you have written on the specs that you require, let's say, 96.5 motor efficiency for the high pressure pump, which is a good value. This is not so bad. is normal value, normally required. 96.1 required by the specs in the low pressure pump, and let's say the same value for the second pass RO high pressure pump. These are motors, as we saw below, about 1 point something megawatts. Let's see, where is that? Okay, 1.2, 1.1, and this high pressure pump is about 6 megawatts. Okay, with these values, we play here with the consumption, and I repeat, just modifying the consumption with all this I told you before, the wire, the losses, the bearings, the fan, the cooling methods, the strategy, the power supplies, and so on, we can consider just to increase the efficiency of the motors. And let's see the impact in this Excel file. If we modify, you see here, there are no savings, consider one price for the kilowatts. If we increase this efficiency energy just for the high pressure pump from 96.5, which is in the specs, to, let's say, and we can achieve that 97 point something, 97.2, look, you can see a very big increase in efficiency, which goes to a lot of savings, considering the cost of the energy, of almost $300,000 or euro per year. And not only that, the specific power consumption has decreased from 3.07 in this example to 3.05 in these conditions, but you can pay the motor is paid by itself. Also, you can do the same for the low pressure pump. Let's say that in this case we reach only 96.5, which is a very good value as well. And the same for the second pass RO. If we modify here to these values, sorry, because of the speed of the internet. Okay, so let's open this for you to see bigger values. Okay, I don't know why you cannot see that. Okay, here we are saving with these slight modifications more than $300,000 or euros per year. This is a lot of savings in cost, but also the efficiency, as I told you before, has decreased a lot. 3.05, 3.07, this difference makes a huge difference when you are studying the financial costs and you have to calculate your tariff. So this is how we can help to increase the efficiency and effectiveness of our proposal for a big contract. We are doing this from the beginning stage, as I told you at the beginning of this presentation, and even more. In this case, you are saving 4.3 gigawatts per year, which is a lot. In my humble opinion, this is quite a big difference. And now that we are always talking about the carbon footprint and environmental issues, this also affects to the CO2 equivalent. With this, the total amount of that, depending on that, considering the equivalence between CO2 and kilowatts hour, we are saving more than 1,000 tons per year in CO2 equivalent. This is the big figures. These are the big figures, and this is the point that we have to consider when you can include these products, this technology, from the conception of the project. We have an holistic view. We can consider many things, and when you are going to fight for a BOT contract, I think this is for the OPEX. This is quite interesting. Let's close this presentation. Let's continue with that. You have seen that for motors. For the drives is the same. Medium voltage drives is the same. This is another example for a big plant. In this case study, considering all the motors fed by drive, all the drives in the plant, we were saving 8.38 gigawatts per year, which is a lot. So consider how big is this contribution. Here we are improving a little bit efficiency. We are having a big savings. So this is the big part of my presentation. I hope this was interesting for you. There are some photos of our equipment and plants. And as I said, less electricity consumption, less carbon footprint. This is a contribution that is made from the outset in engineering with more efficient systems and solutions. Okay, so we have also, just as I told you before, if I have time, Jack, let's take a quick look to some other ideas and solutions for that could be used in these desalination plants. We can have customized drives with different cooling systems. We are developing other alternatives that very soon will be launched to the market. Cooling methods, water or air. We have electrical panels, the house here, which contains the whole electrical room. The whole electrical room you may have in the desalination plant. We can assemble it in the factory, test it in the factory, and send it to the site, which saves a lot of money, a lot of time. We have energy recovery systems based on storage systems with batteries and generators and to return energy to the desalination plant. Optimization in motor and drive by designing with 60 frequency concept. When we design the motors with a drive and we put this in the exact rotating speed for the operating point, instead of the standard 50S or 60S, whatever, you are reducing a lot the size of the motor, consequently the price, and you avoid the impacts on the current to calculate the frequency converter. So you don't have to rise too much. Here in the curves, well, this is a more specific details, but with this definition, you go to the required proper point, okay? We have other solutions, the Pump Genius solution, which is a special function that turns your standard frequency converter, your standard drive, into a controller for the pumping system. We have different modules here, software, energy saving, pipe filling mode, dry pump protection, pump cavitation monitoring, pipe burst alarm even. You can monitor when there's a leakage, when the pump is broken. Another solutions, well, this is the future, okay? Because we also invest heavily in R&D, in research and development. Normally, our concept of the business, we seek to make rational use of resources. We use a rational use of resources. We got new materials and increase the efficiency. We develop induction motor here, the big one, the big blue, but also transversal and axial flux motor. This one is an axial flux motor. This is not developed already for the water industry, but the comparison is big. Here you see in the top this density, kilowatts per kilo. In induction motor typically is 0.15, 17, whatever, and is more than 4 kilos per kilogram. So 4 kilowatts per kilo in this induction motor here. So who knows? Maybe one day we will see adapted to our sector. And also, for sure, just to finish this presentation, the digital business, motion fleet management, we have these modules, digital intelligence, machine learning, and so on. We monitor and we have this to support maintenance and operation. We diagnose the failures, the unbalance, the bearings failures, everything related to maintenance for the rotating equipment. And we can see here we have an energy submodule where we can check and we determine the module, the operating point and the consumption. For me, what can be very useful in this motion fleet management solution is if in a water treatment plant, we use that feedback to learn from plants that are already in operation. And we use this feedback in future designs to optimize it. Okay, this is the important thing, and it's something, could be another webinar or could be something more interesting. But all this smart solution, I give you just a quick glance. So, well, that's all for now. I hope you liked the presentation. I hope you didn't find it too boring, and maybe you have some interesting aspects or ideas for you. You know that you can contact us if you have any question for desalination plans. Thank you very much, and I will like to give you a short video for our seminar, if I can do that, Jack. It's a short video.
We're just
We
about
use
over the
maybe,
35 minutes.
yeah,
Jesus,
we are too much. Maybe you can present later.
or send a link that we can look at
Yeah.
after the webinar.
Okay, you have here
Okay.
the link in YouTube link, and you can check it later. Or if we can have time, it's only 1.5 minutes. You can see it later.
Okay. So thank you
Okay,
very much,
so-
Jesus, for your talk. There is a question. Hussein asks,
Thank you.
do you have performed analysis of energy saving about CapEx and OpEx and how it affects the competition of price for turnkey projects?
The CapEx and OpEx, you mean? Well, the CapEx and OpEx is the difference is impressive because normally we are always buying motors, okay, and you say, okay, this is very expensive. We are always talking about the price of the components. That's sure, for an EPC I can understand that, but normally the CapEx of the motor represents 5% of the total cost of the cost of the motor for the EPC. 5%, let's say that less than 5% is the cost of the motor itself. The other is the maintenance and the energy consumption. So this is a big issue. It's like an iceberg, you know. The point of the iceberg, the top is the cost, but below that is the OpEx, the operation. You have seen in the Excel file, you modify, how can you increase the reduction in OpEx?
So just to follow up on Hussein's question, then in that case, it pays to be able to reduce energy and OpEx and maintenance by investing more in special kinds of motors and electrical infrastructure that is at the base of the overall plant.
Yes, for sure. Jack, for you to understand, or for the audience, when we talk about low voltage motors, we are talking about the standards, IE3, IE4. We have even developed even IE, which is under IE7. But normally, you replace one IE2 motor or one IE3 with IE4 or IE5 standard, you are saving a lot of money. We have even power calculators that you can see the energy savings that gives you the price that you are saving. So the motor is paid by this modification. You replace one IE3 motor with an IE4 motor, the cost is paid in less than 1 year. So this is different. That is different. This is for low voltage motors. Imagine if we can do that for high voltage motors, which are made to measure. You saw 96.5 compared with 97.2. The price difference is less than 1 year or 2 years amortization.
Okay, thank you. Does anyone else have a question? We have time for one more question on the chat if someone wants to put it up. Okay, wait just a second. Go ahead, Sonu Dul.
I have a question. Is it economical to use the VFD with the bypass for the motor which is running on the maximum frequency process point of view?
The question is whether it makes sense to use a bypass.
Yeah, whether it's used, it's economical for use a dual bypass or star delta bypass, whatever it is, to reduce the VFD losses in a system for the energy efficiency.
To make a bypass to the drive, you mean?
Yeah.
Yes, you can use a bypass to the drive, but what happened? You bypass, the motor has to run at the 50 Hz frequency. So normally when we design a motor and drive, it's because they are not operating at the line frequency and the standard frequency. So If you are talking that before I talk about the safety frequency design, is because, for instance, in the pumping station, you have one pump running at 50 Hertz, okay? You select the point and you can have a soft starter or DOL motor, and that's okay. But if you have a drive and a motor with the safety concept, safety frequency design concept, you can put this motor operating at 43 Hertz, for instance, for example. 43 Hertz means with this drive that the motor is smaller because the iron is smaller, you have less losses, and at the same time, the frequency drive fits to keep this motor in operation. For sure, it's going to have a loss in efficiency because it has efficiency, this drive about 98%, so 2% is losses. But if you are bypassing these losses, you get the motor to 50 Hertz with not so good efficiency. So you have to balance both options. But sometimes it happens. You can take the decision to run this at 50 Hertz. If you bypass the drive, you eliminate these losses, yes, but you are not operating in the proper point. So this depends of your design and the operating mode. The functional description will decide, okay, let's bypass this because we don't need to be so accurate in the operating point. Could be.
Okay.
And this is when you have a back
Jesus,
pressure.
I'm going to suggest that this is getting into quite detail. So I would suggest that Sonu and you be in touch directly with Jesus so that you can go into more detailed discussion, because I think that this is actually a more detailed issue. Meanwhile, I want to again thank Jesus for giving us a very detailed overview of opportunities in the mechanical and electrical side of how to get improved efficiency in the desalination plants. So thank you again. So
Thank you to you.
So we're going to move on now to the next talk. The next talk will be given by Juan Cifuentas, who is the technical manager of ERI, which is a very well-known energy recovery company in the desalination field. He has worked with EPCs in both construction operation and maintenance management for a number of years, and been worked on a number of desalination plant projects around the world. He's got a master's in chemical engineering from the University of Oviedo, and I'll turn the floor over to you, Juan. Thank you.
Thank you very much, Jack. Thank you also. I want to thank also Miriam and Israeli Desalination Society for inviting me. It's an honor of being here. Also, thank you all for being here to attend this webinar. And let's see if I can make it somehow interesting for all of you. So we're going to talk about the energy recovery solutions for low pressure reverse osmosis systems in wastewater and desalination. Okay. The agenda is one introduction about low pressure reverse osmosis systems, introduction to the PX pressure exchangers device, how we can design low pressure reverse osmosis systems with the PX, what kind of retrofits we can do with these ERDs, with these energy recovery devices, which energy savings we can achieve with in low pressure systems, and a couple of references that have already been done. So, what's low pressure reverse osmosis? It is a water treatment system that uses reverse osmosis technology in low salinity waters, low TDS, that makes it to operate below normally 27.5 bar for 100 psi and normal at higher recoveries. In this case, a high pressure pump supplies the 100% of the feed or the water treated through the membranes, and a certain amount, 15 to 35% of the energy is wasted by a valve in the reject. Which are the main applications? Water reuse, brackish water reverse osmosis, and wastewater treatment. As commented, it is a low TDS, normally below 15,000 ppms. And it makes that it is possible to achieve recoveries up to 85%. Normal recoveries in these systems go beyond between 65 to 85%. It means also that you normally have to use 2 or 3 stages systems, as normally one stage system can only go up to 50%. Also, as commented, up to 35% of the energy is wasted through the brine control valve, and they normally have several operating conditions because the water is very variable. The challenges this system has are the high recovery rate that could develop in reduction of permeate, uneven falling between stages, and reduction of the feed flow. Also, as in any other reverse osmosis system, power limitations or power cost make it a challenging system. Brine disposal is nowadays even more important because government regulations don't allow a lot of disposal of brine, so it is also challenging. And mainly the uneven hydraulic balance across the multiple stages that makes difficult the operation and maintenance. So if we are not using ERDs, we are not minimizing the OPEX. From 55 to 35% of the energy is wasted through the brine valve. Sorry. And because 100% of the water is fed by the high pressure pump, and 35% of the energy is wasted through the brine control valve. So the specific energy consumption of one system, about 4,000 TDS, 75% recovery, low pressure reverse osmosis, is about 0.8 kilowatt hour per cubic meter. In case we use an ERD, an energy recovery device, we can reduce this OPEX, this energy consumption up to 40%. That means about a reduction in the operating expenses of 70%, only the electrical savings. But if we add the savings that we can have reducing the number of CIPs cleaning in place, or even the membrane reposition rate, that is huge in these systems, then the OPEX cost will be much lower. Here you can see that the energy consumption goes from 31% of the total operating expenses to 27% of total operating expenses. But then why they were not used in the past? As these systems are high recovery, low pressure, people were used to say, we are wasting very low amount of energy. So in addition, the return of investment was quite long. So it was normally not interesting. Also, the water reuse was less extended than it is nowadays. So we used to think we had more water than enough. But there have been some triggers that are making these devices more used nowadays. The energy costs, as we all know, the electricity prices have gone up a lot in the recent years. There are some countries where there are power limitations. Also, efficiency and environmental indicators for some companies and also governments. And of course, the water scarcity that makes it necessary to find out how to improve the water use everywhere. In addition, ERDs normally improve the system's reliability and availability. Let's see what's the PX pressure exchangers and how it works. We can modify a low pressure two-stage system from the normal design from high pressure pump and 2 stages. We can introduce an interstage circulation pump and the PX to reduce the specific energy consumption up to 30% or lower as 0.56 kilowatt hour per cubic meter. How it works? The PX takes the hydraulic energy from the brine and transfers it to the feed directly by direct contact of some part of the feed. And it is combined with the high pressure feed developed by the high pressure pump. The booster pump or the interstage booster pump allows us to do the balance between the stages and also overcome the head losses in the two stages. It means that the PX plus the circulation pump works as a parallel pump to the main high pressure pump, reducing the required flow of the high pressure pump just to the permit flow. And what's the PX? Some of you may already know what's the PX. It is in the low pressure system. It is the same proven technology than in the seawater RO. It has just one moving part. That means that we have almost a maintenance-free equipment with the leading reliability, 99.8%. It has an hydrodynamic bearing that also means there is no material-to-material contact, and it has an automatic speed adjustment. So it means we have flexible operation all above the operating range with the highest efficiency. It is manufactured of ceramic components, so it is completely corrosion-free. It is also very durable. It is 3 times harder than steel, and it suffers no fatigue. It is also lightweight and has a small footprint. Also, in terms of design, it is compact and it is modular. It means that we can design any system, no meaning the size it has. We can put PX elements in parallel to achieve the required flow. How does it work? It works as if we have 2 parallel pipes that are in 2 stages, one sealed and one pressure exchange. In the sealed phase, we have one pipe filled with low pressure feed and the other pipe filled with with high pressure feed and with low pressure brine. Then when it rotates, the low pressure brine is put into contact with low pressure feed that moves away the brine. And in the other pipe, we have the low pressure feed that is pressurized and moved by the high pressure brine. Then it spins to the sealed phase, and we have again the low pressure feed, the high pressure, low pressure brine depressurized, and the high pressure feed, the low pressure feed prepared to be again to pressure exchange. As the rotor is continuously spinning, it is done continuously without the use of any valve and without any losses. What design considerations we have to take? In a multi-stage reverse osmosis systems, as we usually have in low pressure, we need to balance the fluxes between the stages. We have a better fooling control. We have therefore a reduced CIP frequency and an increased water availability. Also, we improve the quality of the second stage, and normally the total permit quality is improved. And also we have normally a lower required feed pressure. As you can see here, membranes fouling are quite one of the most important problems in the reverse osmosis, and also it happens in the 2-stage low pressure systems, where not only fouling but also scaling in the second stage is a very big problem. So we have very common design configuration that is a non-flux balance. In this case, the first elements of the first stage suffer a very high flux. Meanwhile, the tail elements on the second stage have a very low flux. What we can do? What we can use a throttling valve in the first stage permit. In this case, we increase the pressure in the permit of the first stage, making the feed go to the second stage. Therefore, we produce less in the first stage and move the production to the second stage. And we improve all the fluxes in the pressure vessel. And then, if we add an interstage boost, what we can achieve is the same flux distribution, but the high pressure pump has just to provide the pressure required in the first stage, and the interstage boost pump only pressurizes the second stage feed. Therefore, we are further improving the efficiency of the system. If we then include the PX device, the energy recovery device, we have the two-stage system with interstage booster pump and the PX. The booster pump provides the required interstage boost and also the hydraulic losses in the system. And then it controls also the concentrate pressure, as then it is we can achieve with the PX the required pressure at the membrane feeds in the first stage. In case this pressure is too high, we can set a pressure control valve of the outlet of the PX in the high pressure outlet to reduce this pressure to the membrane feed and to control the production. And as commented, the high pressure pump flow has been reduced just to the permit flow. Which are the advantages of this system? We are using the highest efficiency ERD. We improve the control and the balance of fluxes of the system. It is a very simple integration, just a pump and the PXs. And also, we can operate in a wide range of operating conditions because the PX can operate in a very wide range of pressure and flows with a very low impact in the efficiency. Finally, we are reducing the high pressure pump size. So, as commented, with interstage boost, we can balance the hydraulic between the stages. So, we using the boost on permit throttling. But if we also add the PX devices, we are maximizing the OPEX savings. Also, we are, in this case, in all the cases, increasing the lifespan of the membranes. Finally, regarding the PX, this is the energy recovery device that has the maximum flexibility. As if we compare this device with the turbocharger, we can see that the efficiency is almost the same all around the allowable flow. However, the efficiency in one turbocharger varies a lot in the small operating range of this device. Therefore, we have much more availability of operating points with this device. How can we retrofit an existing system with ERDs? We can require to increase the permit flow. Normally, if you have to increase the permit flow, you have to increase the number of pressure vessels, membranes, but you also have to change your high pressure pump. However, if you include the PX device and interstage booster pump, you have just to include these devices because the high pressure pump has just to provide the permit flow. Therefore, with the same high pressure pump flow, we can produce 15 to 35% more depending on the recovery of the system. We also may have to accommodate higher salinity and increased pressure. We may use a turbocharger, or we may use a booster pump also with the PX device, with the booster pump. We also may require to increase the recovery rate. We want to have more water from the same feed. We can again add the PX device with the interstage booster pump. By reducing the flow in the high pressure pump, it will develop a higher head that is normally required for higher recoveries. Then we will not have to change also the high pressure pump. Or we have just to increase the permeate quality. As we commented, if we balance the fluxes between the stages, we are improving the permeate quality. Therefore, including the PX device and the interstage booster pump, we are balancing the flux at the same time that we reduce the operating cost of the plant. And what energy savings we can expect by using the PX energy recovery device, pressure exchanger. If we go to the figures at the beginning of the presentation, in a two-stage configuration, 4,000 ppm FTDS and 75% system recovery, the baseline was about 0.8 kilowatt hour per cubic meter. If we add the PX and we don't use any flux balance or interstage booster pump, we can reduce 26.5% the specific energy consumption. But if we also add the interstage booster pump and we balance the fluxes, as we are operating at the best point of the arrow membranes, we are reducing up to 30% of the specific energy consumption. We can see here how it is affected the savings by the operating pressure and the flow. Logically, as higher as the operating feed pressure is, as more savings we can achieve. Also, the economy of scale makes that as higher flow the system is, as higher savings we may have. With all these figures, and considering $4.15 per kilowatt hour of energy cost, in the past, the payback period was about 4 years. From 4 years to 10 years, the payback of installing the energy recovery devices. However, with the energy costs as they are and improving the systems and the cost in the energy recovery devices, we are going up to 4 years of payback period, but normally lower than 4 years. That's why it is making nowadays more interesting to include the energy recovery devices in these low pressure reverse osmosis systems. Now we can show a couple of references we already have. One is in one plant in Northport. It's a brackish water 8,000 milligrams TDS. It's a little bit tricky because this water can vary a lot in its salinity. That's why we will see later how it is what the savings will be. The incentive to use the ERD, it is clearly the energy price, and it was commissioned in 2022. It is a 2 million gallon per day permit plant in 2 racks and 80% recovery. Just 1 PX 220 per train, and it is to produce drinking water. The savings are expected to be between $11,000 to $105,000 per year. This is the range is so wide just because the salinity is expected to vary a lot along the years. The important thing here is that even when the salinity and pressures and flows of the system will vary a lot along the years, we can still use the same PX model. That's because it can handle a wide range of flow and for sure all operating pressures below 27.5 bar. So at energy cost of $30 cents per kilowatt hour, the return of investment is less than 2 years. And we have another example, another reference, Kona Village. It is also for drinking water and irrigation. And it is a different design, only 55% recovery system, and a smaller size, 1.1 million gallons per day. In this case, the savings are up to $27,000 per train per year, and the return of investment is less than 2 years also. And conclusions. In these low pressure reverse osmosis systems, achieving the hydraulic balance can improve the reliability and reduce the operating cost. The low pressure PX enables these systems to operate at the lowest specific energy consumption possible. Also, it provides flexibility, as commented. We can work at very different operating conditions, and also with consistent performance over this wide operating range. It is more reliable and easier to operate and maintain than on feed waters, and also it is the most reliable energy recovery device in the market. Also, it provides the lowest life cycle cost. Apart from the environmental benefit of the PX, of the energy recovery devices, these savings can also be monetized. There are new energy saving rebates possible as high as 6 cents of dollar per kilowatt hour in California. And also you can sell carbon credits. So PX provides the lowest energy consumption, providing a wide range of operational flexibility, and it makes it the preferred ERD solution to enhance the low pressure reverse osmosis use. Thank you very much for your attention. Any question?
Juan, thank you very much for your talk. There are questions that were asked. The first one you already answered. Shaul asked what the energy transfer efficiency of the device is. You showed in your graph there it was 96 to 93%, depending on where you were on the flow line. The second question is from Sadri. She says that they have an experience when they start their RO rack that sometimes the PX device gets stuck. It doesn't rotate due to accumulated salt. Do you have any tips to keep the PX always in good condition so that won't happen?
Yeah, thank you for this good question. Yes, the PX can get stuck. It can stop rotating because it has a hydraulic bearing with a very small space. So any dirt that gets in this bearing can make the PX to stop rotating. To avoid salts being deposited into this bearing, it is mandatory to have a flushing system of the reverse osmosis and the PXs. Furthermore, we normally offer, when we supply the PXs, we offer a P&ID review to any customer we have. And in this P&ID review, we ask for this flushing system. We need to be able to flush the high pressure side and the low pressure side of the PX to avoid this salt deposition in these channels and to be sure that the PX will start rotating again when the system is started up. Of course, if there is biofouling or there is any kind of matter of solids inside the water, it can make the PX to be stuck again. That's why we also require a minimum filtration rate of 20 micron or even 10 micron, depending on the equipment. I hope this answers the question.
Thank you. And so from the audience, there were that was the questions they had, but I'm now going to play devil's advocate with you. You mentioned that your system is isobaric, which
Yep.
means that as you explained, that the outlet feed from the pressure exchanger will often come out at a higher pressure than the inlet pressure to your first stage, because you've got a booster pump between the first and second stage.
Yep.
And so therefore you lose energy on your on throttling between the outlet from the pressure exchanger and the inlet to the first stage. So the first question I have in that connection is, when you allow for that energy loss because you have to throttle, and that will become more significant as you go to higher recoveries and higher osmotic pressures, as that throttling loss becomes higher, is the energy savings from the ERI-PX still significantly better than you would get from having a turbocharger, which has the flexibility of being able to take unequal flows between the feed flow into the second stage and the concentrate flow coming out of the second stage?
Okay. Normally, the efficiency of the PX is normally this always better than the turbocharger efficiency. That's clear. There is no doubt in that case. But it's true that if you have to have this valve throttling at the outlet, it can reduce the savings you have in the PX. You will have to study case by case, but normally also in the turbochargers, if you have in a stressing boost, you have to bypass the turbocharger as well. And therefore, you may be losing energy in this turbocharger bypass. Also,
wait. Can you explain that wasn't clear to me. What would require you to have a bypass on the turbocharger? I understand that turbochargers are flexible enough that they can take any flow into the inlet in order to boost what's coming in from the interstage feed.
The turbocharger is much less flexible in terms of flow and pressure than the PX is. That's clear, because the turbocharger is a combination of turbine and pump. Each of these equipment has its own curve. So we know that the efficiency of one pump and one turbine depends on the pressure and flow operating point. So if we define the turbocharger in one operating point and we slightly modify this point, we are losing efficiency. That's the first thing. And also, in some case, depending on the boost you need in the second stage, maybe, and depending on the reject ratio you have, it means the overall the second stage recovery, you may have excessive boost. And it normally happens when you have lower recovery in the second stage and very high boost, recovery boost, because then you will have a very high amount of energy going out from the reject that the turbocharger cannot put inside the feed of the second stage. Okay, so you will have to check in case by case, but normally at any operating point, normally the PX will always be higher efficiency than the turbocharger.
Okay. We have a question from Miriam. Miriam, you want to ask your question?
Yes. Thank you, Juan, for a very detailed and interesting presentation. How people can make the calculations to look into this design of a RI. And the second question is if you can provide support in cases that we will need to find the optimal design.
Yeah, sure. We have our Power Model Pro, that is a web-based design software that it is the same that you can use for seawater reverse osmosis systems. You have just to sign in this web software, and there you can find the low pressure PXs that are indicated with a B, brackish, and always you have less than 27.5 bar in the brine pressure, you may select these low pressure devices. So the design will be as it is in the seawater reverse osmosis, and with the same software that is quite friendly and you can use it. If you go to energyrecovery.com, you can find there the Power Model Pro website where you can sign in and enter the software.
Excellent. Thank you very much.
Of course, my team, Rolando Bosleman and I, will be happy to support you, to help you in case you want to do any kind of design, to try it, to see the value proposition, which are the savings you may have.
Perfect. Thank you very much.
I have, Juan, I have one more devil's advocate question for you.
Yep.
There was the question about the salt before, but one of the things that we know that it's a major operating issues when we're talking about brackish water desalination is as you get into the high recoveries, you of course get the very high supersaturations of sparingly soluble salts. It is true that they are managed with antiscalants, but the question is, does one have to be concerned with the potential for scaling on the rotors from these supersaturated salts if you're feeding BWRO concentrate into the ERIPX pressure exchanger?
I think we have already discussed this topic because we have been discussing with people working with ultra high pressure systems with very high salinity systems, the total opposite systems in terms of pressure. And in this case, okay, we are concerned about the scaling, but more than scaling about the suspended solids, okay? So what happens if there is precipitation? Okay, of course, we are concerned about that. But if we are having precipitation in the second stage membranes, we think that the main problem will not be the PX, but will be the membranes itself. Because if we have precipitation that are affecting our PX, membranes will be suffering much more than our PX, okay? So we do not expect scaling during operation because there will be flow, so there will be no stagnant point during operation, so we are not expecting having problems. Meanwhile, you are not having problems in the membranes, okay? The problems with salts deposition or scaling can happen in case you have stagnant water with very high salinity, with high concentration of salts that could be then could precipitate and could start the rotor. But during operation, it is not expected to have this kind of problems.
Okay, good. If you could, if there are additional case studies beyond the ones that you presented in your talk, I think people would be interested to follow up on that. So if you could provide links to more case studies, I think we would all appreciate it.
I will try. Also, we are now working in one very big project in United Arab Emirates. It's a recycling wastewater. It is a very big system. Also, a quite common application is nanofiltration. Also, low pressure reverse osmosis. It's different. It's at the end of the day, it's the same in terms of pressure. It's different because you are removing only one type of ions. But I will look for these other references and case studies, and I will share through Miriam, through the Real Desalination Society.
Excellent. Juan, thank you very much for your really interesting talk. And I want to thank both you and Jesus for providing a window on opportunities for doing energy savings, which of course is such an important issue, certainly when we think about the climate warming issues that we all have to deal with as we go forward. So I'm going to turn it back over to Miriam that you can wrap it up for today's webinar.
Thank you very much, Jack. for moderating, for the questions, for the interesting questions. I will lower my hand. And I want to thank Jesus and Juan. Muchas gracias. It was really two excellent presentations. And I'm sure people will digest a little bit all the information. And we will be glad if we can send you additional questions, and you will be in touch with the people of the audience as well. So thank you very, very much. Thank you very much to all the participants. And we will be publishing shortly our next webinars. And Juan and Jesus, you are also invited to our next webinars as well. And have a good evening, and thank you a lot for being with us. Bye-bye.
You're more than welcome, Miriam. Thank you very much for the organization. Thank you to you for this opportunity. Great. Excellent.
Thank you.
Thank you very
Bye-bye.
much.
Thank you. Bye-bye. Thank you. Bye.
Thank you, Jack, as well. Bye-bye.